Imagine standing in the heart of León, the sun's searing light suddenly snuffed out by the moon's shadow, leaving only the ghostly glow of its corona, a shimmering halo of plasma that reveals the sun's secrets hidden by daylight. This is the magic of a total solar eclipse, a fleeting moment when the cosmos stages its most dramatic spectacle. But here, in this Spanish city, something extraordinary happens. The European Space Agency, the University of León, and local scientists join forces to turn this ancient wonder into a modern scientific adventure. They're not just watching the sky, they're decoding the sun's mysteries, using cutting-edge instruments to capture data that could reshape our understanding of stellar physics. As the moon's shadow sweeps across the landscape, the air grows cooler, the sky darkens, and for a breathless minute, the universe pauses. This isn't just a celestial event, it's a collaboration between centuries-old astronomy and tomorrow's science, unfolding in the quiet streets of a city that's become a beacon for the curious. During a rare celestial event, scientists and citizens came together to witness a total solar eclipse, offering a unique opportunity to study the sun's mysteries. This total solar eclipse, observed in León, Spain, was more than a spectacle, it was a scientific milestone. The collaboration between the European Space Agency, ESA, the City of León, and the University of León transformed the experience into a blend of public engagement and cutting-edge research. At the heart of this event was a fundamental question: how does the sun's atmosphere behave under extreme conditions? The answer lay in the fleeting moments of totality, when the sun's corona, a luminous halo of plasma, became visible, revealing secrets hidden by the sun's blinding brightness. This chapter explores how this eclipse became a window into the sun's complex physics and the role of collaboration in advancing scientific understanding. Total solar eclipses are among the most awe-inspiring natural phenomena, but their scientific value lies in the brief window when the moon completely blocks the sun's disk. During this time, the sun's corona, which is usually obscured by the sun's intense light, becomes visible. This corona is a region of superheated plasma, millions of degrees Celsius, that extends millions of kilometers from the sun's surface. Studying it provides critical insights into the sun's magnetic fields, solar wind, and the processes that drive space weather. However, observing the corona is challenging because it is faint compared to the sun's visible light. The total eclipse, lasting just a few minutes, offers a rare chance to study this elusive region in detail. For scientists, this event was a unique opportunity to gather data that could refine existing models of solar activity and test new hypotheses about the sun's behavior. The collaboration between ESA, the City of León, and the University of León ensured that this scientific opportunity was both accessible and impactful. ESA, with its expertise in space science and satellite technology, provided the tools and knowledge to analyze the eclipse's phenomena. The City of León played a vital role in organizing public events, ensuring that the community could safely witness the eclipse and learn about its significance. The University of León contributed by coordinating local scientists, educators, and students, turning the event into an educational experience. Together, these institutions created a seamless blend of scientific research and public engagement, demonstrating how space science can bridge the gap between experts and the general public. One of the primary scientific goals of the eclipse observation was to study the sun's corona using ground-based instruments. While space telescopes like NASA's Solar Dynamics Observatory and ESA's Solar Orbiter have provided valuable data, ground-based observations during an eclipse offer a unique perspective. During totality, researchers could use specialized equipment to capture high-resolution images and spectra of the corona, measuring its temperature, density, and magnetic field structure. These measurements are crucial for understanding how energy is transported from the sun's surface to its outer atmosphere, a process that remains one of the greatest mysteries in solar physics. By comparing data from the eclipse with observations from space, scientists can validate models and refine their understanding of solar dynamics. Another key aspect of the event was the testing of solar models that predict the sun's behavior. These models are essential for forecasting solar storms, which can disrupt satellite communications, power grids, and navigation systems. During the eclipse, researchers used the corona's visible features to test the accuracy of these models. For example, the corona's brightness and structure are influenced by the sun's magnetic field, which is generated by complex interactions between plasma and magnetic forces. By analyzing how the corona appeared during the eclipse, scientists could assess whether their models accurately represented these processes. Such comparisons help improve predictive capabilities, ensuring that future space weather forecasts are more reliable and precise. Beyond its scientific value, the eclipse event highlighted the importance of public participation in space science. The City of León organized viewing events in public spaces, allowing thousands of residents to witness the eclipse safely. These events were not just about observation, they were about education. Local educators and students engaged with the community, explaining the science behind the eclipse and its relevance to everyday life. The University of León hosted workshops and lectures, where experts shared insights into the sun's role in the solar system and the technologies used to study it. This approach transformed the eclipse into a platform for science communication, inspiring curiosity and fostering a deeper appreciation for astronomy. The collaboration between ESA, the City of León, and the University of León also underscored the power of interdisciplinary teamwork. Space agencies, local governments, and academic institutions each brought unique strengths to the event. ESA provided access to advanced instruments and data analysis techniques, while the City of León ensured that the event was accessible to all. The University of León bridged the gap between research and education, making complex scientific concepts understandable to the public. This synergy demonstrated how diverse partnerships can amplify the impact of scientific discoveries, turning a single celestial event into a catalyst for broader engagement with science. The eclipse also served as a reminder of the sun's profound influence on our planet. The corona's extreme temperatures and dynamic behavior are linked to phenomena such as solar flares and coronal mass ejections, which can affect Earth's magnetosphere and space weather. By studying these processes during the eclipse, scientists gained valuable data to better understand their effects on technology and communication systems. This knowledge is critical for developing strategies to mitigate the risks posed by space weather, ensuring that society can prepare for and respond to solar events with greater resilience. In addition to its scientific and educational contributions, the eclipse event in León symbolized the growing trend of public science engagement. As space agencies and institutions increasingly recognize the value of involving the public in their work, events like this eclipse become more than just observations, they become opportunities for dialogue, collaboration, and inspiration. The enthusiasm of the community, combined with the expertise of scientists, created a vibrant atmosphere of curiosity and discovery. This kind of engagement is essential for sustaining public interest in science and ensuring that the next generation of researchers is inspired to explore the cosmos. The collaboration between ESA, the City of León, and the University of León during the eclipse exemplifies how science can be both accessible and transformative. By combining cutting-edge research with community involvement, the event highlighted the sun's role in our solar system and the importance of understanding its behavior. The data collected during the eclipse will continue to inform scientific studies for years to come, contributing to our broader understanding of the sun and its impact on Earth. As we reflect on this extraordinary event, it becomes clear that total solar eclipses are not just moments of natural wonder, they are vital opportunities to advance human knowledge and connect with the universe. The total solar eclipse is more than a celestial spectacle, it's a moment of profound scientific significance. For centuries, astronomers have studied these events to unlock secrets about our sun, its corona, and the forces that shape our solar system. But how did scientists predict this particular eclipse, and what tools did they use to observe it with such precision? The answer lies in a combination of centuries-old celestial mechanics, cutting-edge technology, and the collaborative efforts of institutions like the European Space Agency, the City of León, and the University of León. Let's trace the journey from the first calculations to the final moments of totality. At the heart of this endeavor is the science of eclipses themselves. A total solar eclipse occurs when the moon passes directly between the Earth and the sun, casting a shadow that darkens the sky for a brief window. The path of totality, where the sun is completely obscured, is narrow, often just a few hundred kilometers wide. Predicting this path requires precise calculations of the moon's orbit, Earth's rotation, and the relative positions of the two bodies. These calculations date back to ancient times, with early astronomers like Hipparchus and Ptolemy developing methods to track celestial movements. However, modern predictions rely on advanced mathematical models and orbital mechanics, refined over centuries. The European Space Agency's involvement in this eclipse was not just about observation, it was about leveraging decades of space-based research to understand how the sun behaves during these rare events. One of the key tools in this scientific pursuit is the coronagraph, an instrument designed to study the sun's corona, the outer atmosphere that becomes visible only during an eclipse. Coronagraphs work by blocking the sun's bright light with a mask, allowing astronomers to observe the faint glow of the corona. This technology has its roots in the early 20th century, but it has evolved dramatically with the advent of space telescopes. The Solar and Heliospheric Observatory, SOHO, launched by ESA and NASA in 1995, was one of the first missions to use a coronagraph to study the sun in real time. Data from SOHO and other missions like the Solar Dynamics Observatory, SDO, provided critical insights into the sun's behavior, including how solar flares and coronal mass ejections propagate through space. These observations helped scientists model the sun's magnetic field and predict how it might interact with the Earth during an eclipse. For the León eclipse, these models were essential in determining the precise timing and location of totality, ensuring that ground-based instruments could capture the event with maximum accuracy. The collaboration between ESA, the City of León, and the University of León was a testament to the power of interdisciplinary science. The City of León played a vital role in organizing the event, ensuring that the local community had access to safe viewing methods and educational resources. The University of León, meanwhile, contributed expertise in solar physics and public engagement, helping to translate complex scientific concepts into accessible content for the public. This partnership was not just about observation, it was about making science tangible. For example, the University of León developed interactive simulations that allowed people to visualize the sun's corona and understand how eclipses occur. These tools were crucial in preparing the public for the event, ensuring that observers could appreciate the scientific significance of what they were witnessing. The instruments used to observe the eclipse were as diverse as the science they aimed to uncover. Ground-based telescopes equipped with high-resolution cameras and spectrographs played a central role. Spectrographs, which analyze the light from celestial objects, allowed scientists to study the composition of the sun's corona. By breaking sunlight into its component wavelengths, these instruments revealed the presence of ionized gases and their temperatures, providing data that could be compared with space-based observations. Meanwhile, high-speed cameras captured the dynamic changes in the corona as the moon's shadow moved across the sun's surface. These cameras operated at frame rates far beyond what the human eye could perceive, enabling scientists to study phenomena like solar prominences and coronal loops in unprecedented detail. ESA's contribution extended beyond ground-based instruments. Space missions like the Solar Orbiter, launched in 2020, provided a unique vantage point for studying the sun. The Solar Orbiter's instruments, including its extreme ultraviolet imager and magnetometer, allowed scientists to observe the sun's corona from a distance, complementing the data collected during the eclipse. These observations were critical for calibrating ground-based measurements and understanding how the sun's activity varies over time. For instance, the Solar Orbiter's data helped scientists predict how the sun's magnetic field might influence the Earth's magnetosphere during the eclipse, a factor that could affect satellite communications and power grids. By combining data from space and ground-based observatories, scientists could create a more comprehensive picture of the sun's behavior during these rare events. The timeline leading up to the eclipse was a carefully orchestrated process. Months before the event, scientists used predictive models to determine the exact path of totality. These models incorporated data from past eclipses, orbital mechanics, and the gravitational influences of other celestial bodies. The accuracy of these predictions was crucial, as even small errors could shift the path of totality by hundreds of kilometers. Once the path was confirmed, teams began preparing their instruments, testing equipment, and coordinating with local authorities to ensure safe viewing conditions. The City of León, for example, worked with ESA to set up observation sites, ensuring that both scientists and the public had access to the best viewing locations. On the day of the eclipse, the process of observation was a blend of science and spectacle. Ground-based telescopes were set up in strategic locations, their lenses and sensors calibrated to capture the sun's corona at the precise moment of totality. Spectrographs recorded the light spectrum, while high-speed cameras captured the rapid changes in the sun's atmosphere. Meanwhile, ESA's space-based instruments continued to monitor the sun, providing a continuous stream of data that could be compared with ground observations. This multifaceted approach allowed scientists to cross-check their findings, ensuring that the data was accurate and reliable. But collaboration between different institutions was evident in every step of the process, from the initial calculations to the final analysis of the data. The significance of this eclipse extended beyond a single event. The data collected during the observation contributed to a broader understanding of the Sun's behavior, with implications for space weather, climate studies, and the development of solar physics models. For example, the study of the corona during an eclipse provided insights into the mechanisms that heat the Sun's atmosphere, a question that has puzzled scientists for decades. By analyzing the temperature and density of the corona, researchers could refine their models of solar activity and improve predictions of solar storms that could impact Earth. These findings were not just academic, they had real-world applications, from protecting satellites to ensuring the reliability of power grids. The collaboration between ESA, the City of León, and the University of León also highlighted the importance of public engagement in science. By involving the local community in the observation process, the event became an opportunity to educate and inspire. Schools, universities, and citizen scientists participated in the eclipse observation, using the event as a platform to discuss the science behind eclipses and the role of space missions in advancing our understanding of the universe. This engagement was crucial in bridging the gap between scientific research and public awareness, demonstrating how even a rare celestial event could serve as a gateway to deeper scientific exploration. In the end, the total solar eclipse in León was more than a moment of darkness and light, it was a testament to human curiosity and the power of collaboration. The instruments, telescopes, and missions that made this observation possible were the result of decades of scientific advancement, each contributing to a greater understanding of the cosmos. As the Sun emerged from behind the Moon, the data collected during the event continued to shape our knowledge of the Sun, its corona, and the forces that govern our solar system. This eclipse was not just a spectacle, it was a milestone in the ongoing quest to unravel the mysteries of the universe. When the Moon passes directly between the Earth and the Sun, it casts a shadow on our planet, a shadow that can stretch thousands of kilometers. This is the moment of a total solar eclipse, a celestial dance of perfect alignment that reveals secrets hidden in the Sun's brilliance. But why does this happen? And why does it matter? The answer lies in the delicate balance of gravity, motion, and light that governs our universe. The Sun, a massive fusion reactor at the center of our solar system, emits light that travels 150 million kilometers to reach us. The Moon, orbiting Earth at an average distance of 384,400 kilometers, appears just the right size to cover the Sun's disk entirely when the two bodies align. This alignment is not a coincidence, it's a result of the Moon's orbital path, which is tilted relative to Earth's orbit around the Sun. Most of the time, the Moon's shadow misses Earth entirely, but when the conditions are just right, the shadow falls on our planet, creating a fleeting moment of darkness. This event, happening in León, is a rare opportunity to witness this cosmic choreography and to study the Sun in ways that are otherwise impossible. The significance of a total solar eclipse extends far beyond the dramatic spectacle. For centuries, eclipses have been a gateway to understanding the universe. When the Sun's light is blocked, its outer atmosphere, the corona, becomes visible. This halo of plasma, usually drowned out by the Sun's intense brightness, reveals intricate structures and magnetic activity that scientists study to unravel the Sun's behavior. The corona's temperature, for instance, is millions of degrees hotter than the Sun's surface, a mystery that has puzzled physicists for decades. Observing it during an eclipse provides a rare chance to gather data on this phenomenon. Moreover, eclipses offer a natural laboratory to test theories of gravity and light. During totality, the Sun's light bends around the Moon, a phenomenon predicted by Einstein's theory of general relativity. These observations have historically confirmed the validity of such theories, reinforcing our understanding of the cosmos. The collaboration between ESA, the City of León, and the University of León is more than a celebration of science, it's a testament to how such events bridge the gap between public engagement and cutting-edge research. By bringing together institutions, researchers, and the community, this event highlights the importance of accessibility in science. The Sun's corona, for example, is not just a scientific curiosity, it plays a critical role in space weather. Solar flares and coronal mass ejections, which originate in the corona, can disrupt satellite communications, power grids, and even pose risks to astronauts. Understanding these processes is essential for predicting and mitigating their effects. Yet, studying the corona requires conditions that are almost impossible to replicate in a lab. A total solar eclipse provides a unique window into this region, allowing scientists to observe its dynamics in real time. The data collected during such events contribute to models that help forecast space weather, protecting both technology and human activities in space. The rarity of total eclipses also underscores the importance of every opportunity to observe them. The path of totality, a narrow band where the sun is completely obscured, is only a few hundred kilometers wide, and it moves across the Earth's surface at a speed of about 1,700 kilometers per hour. This means that only a small portion of the world can experience the full phenomenon, making each eclipse a fleeting and precious moment. The collaboration in León is a reminder that such events are not just natural phenomena but also milestones in scientific exploration. By combining the expertise of ESA, the local community, and academic institutions, the event becomes a platform for education and discovery. The University of León, for instance, may use this occasion to engage students and the public in discussions about astronomy, while ESA's involvement ensures that the observations made during the eclipse contribute to broader scientific goals. This synergy between local and global efforts exemplifies how science thrives when it is shared and accessible. The study of solar eclipses also has historical roots. Ancient civilizations, from the Babylonians to the Chinese, meticulously recorded eclipses, using them to refine calendars and understand celestial mechanics. These early observations laid the groundwork for modern astronomy, demonstrating that even the most ancient cultures recognized the significance of these events. Today, the same curiosity drives scientists to seek answers about the universe. The Sun, our nearest star, is a key to understanding stellar evolution and the life cycles of stars. By studying its behavior during an eclipse, researchers gain insights into processes that occur in other stars and even in distant galaxies. The corona's magnetic fields, for example, are believed to be similar to those of other stars, making the Sun a valuable model for astrophysical research. Furthermore, the alignment of the Moon and Sun during an eclipse is a reminder of the intricate relationships between celestial bodies. The Moon's gravitational pull influences Earth's tides, while the Sun's energy drives our climate. These interactions are part of a larger cosmic web that connects all planets, stars, and galaxies. Observing an eclipse is a way to appreciate the scale and complexity of the universe, even as it unfolds in a single, brief moment. The collaboration in León also highlights the role of technology in modern astronomy. Instruments like coronagraphs, which block the sun's light to study the corona, have evolved over centuries, from simple pinholes to sophisticated space-based observatories. ESA's involvement in this event may include deploying such technologies to capture high-resolution images and data, which can then be analyzed to deepen our understanding of solar physics. These observations are not just academic, they have practical applications. For example, understanding the sun's magnetic activity helps predict solar storms that could affect satellites and power grids on Earth. By studying the corona during an eclipse, scientists can refine models that improve our ability to forecast these events, ensuring that we are better prepared for their impacts. The significance of a total solar eclipse also lies in its ability to inspire wonder and curiosity. In an age where scientific literacy is increasingly important, events like this serve as a reminder of the beauty and mystery of the universe. The experience of totality, a moment when day turns to darkness, and the sky darkens to the color of a deep ocean, can be transformative. It encourages people to look up, to question, and to seek knowledge. This is why collaborations like the one in León are so vital. They bring science to the public, making complex concepts accessible and fostering a sense of shared discovery. The Sun, the Moon, and Earth are not just objects in the sky, they are part of a dynamic system that has shaped life on our planet. By studying eclipses, we gain a deeper appreciation for the forces that govern our world and the universe beyond. The collaboration between ESA, the City of León, and the University of León is more than an event, it's a celebration of humanity's enduring quest to understand the cosmos. It is a reminder that science is not confined to laboratories or textbooks, it is alive in the moments when we witness the extraordinary, when we see the sun's corona shimmering in the darkness, and when we realize that we are part of a universe that is both vast and connected. For millennia, solar eclipses have captivated human imagination, serving as both celestial spectacles and profound mysteries. Long before the advent of modern science, ancient civilizations across the globe interpreted these events as omens, divine messages, or signs of cosmic balance. The Babylonians, for instance, meticulously recorded eclipses as early as the 8th century BCE, developing predictive models that allowed them to anticipate these phenomena with astonishing accuracy. Similarly, the Chinese, Egyptians, and Mayans wove eclipses into their mythologies, often attributing them to celestial battles or the wrath of gods. These early observations, though rooted in superstition, laid the groundwork for humanity's enduring fascination with the sun and its interactions with the moon. Yet, it wasn't until the scientific revolution that eclipses began to be understood not as supernatural events, but as predictable phenomena governed by the laws of physics. This shift in perspective marked the beginning of a deeper, more systematic exploration of the cosmos, a journey that would span centuries and ultimately lead to the collaborative efforts of institutions like the European Space Agency, the City of León, and the University of León in bringing the wonder of a total solar eclipse to the modern world. The scientific revolution of the 16th and 17th centuries brought a paradigm shift in how humans perceived the universe. Figures like Galileo Galilei and Isaac Newton dismantled the geocentric view of the cosmos, replacing it with heliocentrism and the laws of motion. These discoveries laid the foundation for understanding celestial mechanics, including the precise orbits of the Earth and Moon. By the 18th century, astronomers had begun to calculate the timing and paths of eclipses with remarkable precision, transforming them from unpredictable cosmic events into predictable natural phenomena. This newfound ability to forecast eclipses was not merely an academic exercise, it had practical implications. For example, the 1769 transit of Venus, observed by scientists across the globe, provided critical data for calculating the distance to the Sun, a feat that would later underpin the development of modern astronomy. Yet, even as eclipses became more predictable, their scientific value remained largely untapped. The Sun's corona, the luminous halo visible only during a total eclipse, remained an enigma, a region of the Sun's atmosphere that was both intensely hot and poorly understood. It was during the 19th century that this mystery began to unravel, thanks to the ingenuity of astronomers and the advent of new observational tools. The 19th century witnessed a surge in scientific inquiry into solar phenomena, driven by the realization that eclipses offered a rare opportunity to study the Sun's outer atmosphere. Before this era, the corona was a mystery, its existence was inferred from ancient accounts, but its properties remained elusive. The invention of the spectroscope in the 1850s allowed scientists to analyze the light emitted by the Sun, revealing the presence of ionized gases in the corona. However, it wasn't until the 1860s that the first detailed observations of the corona during a total eclipse were made. These early studies, conducted by astronomers like Angelo Secchi and James Clerk Maxwell, provided crucial insights into the Sun's composition and temperature, yet they were limited by the technology of the time. The challenge of observing the corona during an eclipse was compounded by the fact that such events occurred only in specific regions of the world and were often unpredictable. This scarcity of data meant that each eclipse was a fleeting opportunity to advance scientific knowledge, one that required meticulous planning and collaboration across disciplines. The breakthrough came in the early 20th century, when the study of solar eclipses became a focal point for testing fundamental theories of physics. One of the most significant milestones was the 1919 solar eclipse expedition led by Arthur Eddington, which provided the first empirical evidence supporting Albert Einstein's theory of general relativity. During this eclipse, Eddington and his team observed the bending of starlight around the Sun's massive gravitational field, a prediction that had previously been theoretical. This experiment not only confirmed Einstein's revolutionary ideas but also demonstrated the power of solar eclipses as tools for probing the universe's deepest mysteries. The success of this mission underscored the importance of eclipses in advancing our understanding of gravity, space, and time. It also highlighted the role of international collaboration in scientific discovery, as astronomers from multiple countries coordinated their efforts to capture this historic moment. These early 20th century achievements marked a turning point, transforming solar eclipses from rare celestial events into vital instruments for scientific exploration. As the 20th century progressed, the study of solar eclipses continued to evolve, driven by advancements in technology and the expansion of space science. The mid-20th century saw the development of more sophisticated instruments, such as spectrographs and high-resolution cameras, which allowed astronomers to capture detailed images of the corona and study its dynamic behavior. These observations revealed that the corona is not a static structure but a complex, turbulent region of plasma with temperatures exceeding 1,000,000 degrees Celsius. This extreme heat, far hotter than the Sun's surface, remained a puzzle for decades, prompting researchers to investigate the mechanisms that sustain it. Meanwhile, the launch of the first artificial satellites in the late 1950s and early 1960s opened new avenues for solar research. Satellites like the Solar Radiation and Atmosphere Satellite, SOLRAD, and the Orbiting Solar Observatory, OSO, provided continuous monitoring of the Sun, enabling scientists to study solar activity beyond the confines of eclipses. These missions laid the groundwork for modern space-based solar observatories, such as the Solar and Heliospheric Observatory, SOHO, and the Solar Dynamics Observatory, SDO, which have since provided unprecedented insights into the Sun's behavior. The space age also brought a new perspective on solar eclipses, shifting the focus from rare observations to the study of the Sun as a dynamic, ever-changing star. While ground-based eclipses remain invaluable for certain types of research, such as the study of the corona's magnetic field and solar wind, space-based observatories have revolutionized our ability to monitor the Sun in real time. For example, the Parker Solar Probe, launched in 2018, has ventured closer to the Sun than any previous mission, gathering data on its corona and solar wind. These missions have not only deepened our understanding of the Sun but also highlighted the importance of eclipses as natural laboratories for testing theories and instruments. The data collected during eclipses, combined with space-based observations, has allowed scientists to model the Sun's magnetic field, predict solar storms, and improve our ability to forecast space weather, a critical area of research with implications for satellite technology, communications, and even human space exploration. Despite these advancements, the study of solar eclipses continues to hold a unique place in both science and culture. While modern technology has made it possible to observe the Sun in ways that were once unimaginable, the experience of witnessing a total solar eclipse remains a profound and humbling moment. The sudden darkness, the shimmering corona, and the eerie silence that follows are reminders of the Sun's immense power and the delicate balance of our solar system. This duality between the scientific pursuit of knowledge and the awe-inspiring beauty of an eclipse has driven centuries of exploration, from the earliest observations of ancient civilizations to the cutting-edge research of today. The collaboration between the European Space Agency, the City of León, and the University of León in hosting a total solar eclipse is a testament to this enduring legacy. It is a celebration of humanity's ability to look up at the sky, ask questions, and seek answers through both observation and innovation. As we prepare to witness this event, we are not just observing a celestial phenomenon, we are continuing a story that began thousands of years ago, one that bridges the past, present, and future of our understanding of the universe. As the Sun's light was momentarily swallowed by the Moon, the total solar eclipse over León became more than just a spectacle, it became a window into the universe's deepest mysteries. For centuries, humanity has marveled at eclipses, but today's event was no ordinary observation. It was a carefully orchestrated scientific experiment, led by the European Space Agency, the City of León, and the University of León, aimed at unraveling some of the most perplexing questions in solar physics. Yet, despite the wealth of data collected, many enigmas remain. What forces are responsible for the Sun's corona being millions of degrees hotter than its surface? Why does the solar wind accelerate to such incredible speeds? And how do the Sun's magnetic fields shape the behavior of its atmosphere? These are not just theoretical puzzles, they are questions that could reshape our understanding of the universe. Let's dive into the science behind these unresolved mysteries and the ways in which the eclipse in León might help illuminate them. The Sun's corona, that luminous halo visible only during an eclipse, has long defied explanation. While the Sun's surface, or photosphere, is a searing 5,500 degrees Celsius, the corona reaches temperatures of over 1,000,000 degrees, more than 200 times hotter. This paradox is one of the most enduring mysteries in astrophysics. Scientists have proposed several theories, from magnetic reconnection events to waves of energy propagating through the plasma, but none have fully explained the phenomenon. During the eclipse, ESA's instruments captured high-resolution images of the corona, revealing intricate structures and dynamic movements. These observations could help refine models of how energy is transferred from the Sun's interior to its outer layers. Yet, the exact mechanisms remain elusive. Are the extreme temperatures the result of sudden eruptions of magnetic energy, or is there a steady, underlying process at play? The data from León's eclipse may provide clues, but the answers are still waiting to be discovered. Another mystery lies in the solar wind, a stream of charged particles that flows continuously from the sun's atmosphere. This wind reaches speeds of up to 800 kilometers per second, far exceeding what classical physics predicts. The solar wind's acceleration is a puzzle because the sun's surface is not hot enough to produce such velocities. Scientists believe the wind is driven by magnetic fields, but the precise mechanisms remain unclear. During the eclipse, researchers focused on how the solar wind interacts with the corona, using instruments to measure its speed and density. The event provided a unique opportunity to observe the wind's behavior under extreme conditions, such as the sudden cooling of the corona and the temporary disruption of magnetic fields. Yet, even with these observations, the question of why the solar wind accelerates to such high speeds persists. Is it a combination of magnetic forces and turbulence, or are there unknown processes at play? The data from León's eclipse could help bridge gaps in our understanding, but the answers are not yet in sight. The sun's magnetic field is another enigma that the eclipse helped to probe. The sun's magnetic field is a complex web of lines that governs the behavior of its atmosphere and influences space weather. During the eclipse, ESA's instruments mapped the magnetic field structure in unprecedented detail, revealing patterns that challenge existing models. For instance, the field's configuration in the corona is thought to be shaped by the sun's rotation and convection, but the exact dynamics are still debated. Some scientists argue that the magnetic field is generated by a process called the dynamo effect, while others propose alternative mechanisms. The eclipse provided a rare chance to observe how these magnetic structures evolve in real time, but the full picture remains incomplete. How do these fields interact with the solar wind? What role do they play in the sun's eruptions and coronal mass ejections? The data from León's eclipse may offer new insights, but the answers to these questions are still unfolding. Beyond the sun itself, the eclipse also offered a unique perspective on the Earth's atmosphere. As the moon blocked the sun's light, the sudden darkness and temperature drop created conditions that allowed scientists to study how the Earth's atmosphere responds to such extreme changes. For example, the ionosphere, a layer of the atmosphere charged by solar radiation, can be disrupted during an eclipse, affecting radio communications and satellite signals. Researchers in León monitored these effects, using instruments to track changes in atmospheric density and temperature. Yet, the exact ways in which the eclipse influences the atmosphere are still under investigation. How do these temporary disruptions impact long-term climate patterns? Could they provide clues about the Earth's response to solar variability? While the eclipse offered a glimpse into these processes, the full implications remain a subject of debate. Perhaps the most profound mystery of all lies in the fundamental nature of the sun's energy. The sun's core is a furnace of nuclear fusion, where hydrogen atoms collide to form helium, releasing energy that powers the star. This process is well understood, but the journey of that energy from the core to the surface remains a puzzle. Scientists believe that the energy is transported through a combination of radiation and convection, but the exact mechanisms are still being refined. The eclipse provided an opportunity to study how the sun's energy interacts with its magnetic fields and atmosphere, but the full story of this energy transfer is far from complete. Could the corona's extreme temperatures be a byproduct of this process? Or is there an entirely different mechanism at play? The data from León's eclipse may help answer these questions, but the answers are still waiting to be uncovered. The eclipse in León was more than just a moment of awe, it was a testament to humanity's enduring quest to understand the cosmos. By combining cutting-edge technology with centuries of scientific curiosity, researchers were able to gather data that could shed light on some of the universe's most enduring mysteries. Yet, even with all the observations and measurements, many questions remain. The sun's corona, the solar wind, the magnetic fields, and the Earth's atmosphere all present puzzles that challenge our current understanding. These mysteries are not obstacles, they are invitations to explore, to question, and to imagine new possibilities. As scientists continue to study the data from León's eclipse, they are not just uncovering the secrets of the sun, they are expanding the boundaries of human knowledge. And in doing so, they are reminding us that the universe is still full of wonders waiting to be discovered. Discover the science behind one of nature's most extraordinary phenomena and experience a total solar eclipse with the European Space Agency, ESA, the City of León and the University of León. This part of our deep dive into watch the total solar eclipse with ESA and León focuses on, explain what's coming next, future missions, instruments, or observations that could confirm, extend, or challenge what we know so far. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For viewers who want to go deeper than this summary, the primary source linked in the description lays out the full technical picture. Findings like this rarely stand alone, they get compared against earlier observations to make sure the pattern holds up under scrutiny. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. Discover the science behind one of nature's most extraordinary phenomena and experience a total solar eclipse with the European Space Agency, ESA, the City of León and the University of León. This part of our deep dive into watch the total solar eclipse with ESA and León focuses on, briefly recap the 2 or 3 biggest takeaways from this deep dive in a satisfying way, then invite the viewer to subscribe to FactVerse for daily space deep dives and to comment their own theory or question. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For viewers who want to go deeper than this summary, the primary source linked in the description lays out the full technical picture. Findings like this rarely stand alone, they get compared against earlier observations to make sure the pattern holds up under scrutiny. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable.